Dear students, we all know about solenoid, which is an electromagnet formed by winding wire around a core. Today we shall discuss about a ring-shaped solenoid called toroid. The physicist Michael Faraday invented it in early 1930s. It was Faraday who discovered that a changing magnetic field can induce a voltage in the nearby wire, and this is called Faraday's law of electromagnetic induction. A toroid is a passive electronic component that consists of a circular magnetic core. These cores have high magnetic permeability and are made with iron around which wire is wound. The circular shape of the core helps reduce the loss of magnetic flux, thus making the inductor more efficient. Let us now look at an actual toroid. We have studied about solenoid, which is a straight iron core, the black center, over which the coil is wound. So this is an actual solenoid taken from an electrical circuit. When we take the solenoid and turn it into ring shape, what we get is a toroid. See, this yellow color is the core material over which the wire is wound. So this is how an actual toroid looks like. This figure is the sectional view of a toroid. The black concentric circles represent the toroid. The direction of the magnetic field inside is clockwise. This is as per the right-hand thumb rule for circular loops. The loops drawn in the dotted lines and numbered 1, 2 and 3 are the Amperian loops with radius R1, R2 and R3 respectively. Let the magnetic field along the loop 1 be B1. Then, according to Ampere circuital law, for the length L is equals to 2 pi R1, we have B1 into 2 pi R1 is equals to mu naught into I. Since current enclosed in the loop is 0, therefore B1 is 0. Hence, the magnetic field at any point P in the open space inside the toroid is 0. Now, applying Ampere circuital law to the loop number 3 with radius R3, it passes through the point Q. We have the equation B3 into 2 pi R3 is equals to mu naught into 0. Again, there is no current enclosed, thus I is 0. This gives us B3 is equals to 0. Thus, no field exists at any point outside the toroid. Let us now find the magnetic field at a point S which lies inside the toroid. Using Ampere circuital law for the loop with radius R2, we have B2 into 2 pi R2 is equals to mu naught Ni, where capital N is the total number of turns of the toroidal coil and I is the current flowing. Now, B2 is equal to mu naught Ni upon 2 pi R2. Let us generalize and write the equation as B is equals to mu naught Ni upon 2 pi R. This is the equation for the magnetic field at any point inside a toroid of average radius R. If small n is the number of turns per unit length, then we can write capital N is equal to 2 pi R into small letter n. Thus, we have the equation B is equals to mu naught Ni. In case of a solenoid, the formula is similar, but there it is small n is equals to capital N upon L, that is the number of turns per unit length. Thus, in toroid, due to the ring shape, the magnetic field is much stronger than solenoid at its center. Toroid inductors and transformers are used in wide range of electronic circuits, power supplies, inverters and amplifiers, which are the vital part of electrical gadgets like computers, radio, television, air conditioners, refrigerators and audio systems. Toroidal transformers are favored due to their high efficiency, small size, and light weight. It has a wide use in telecommunication, magnetic field, and musical instruments. A toroid works as an inductor and boosts the frequency to appropriate levels. A guitar amplifier uses toroid to strengthen the weak electrical signals from an electric guitar. Magnetic confinement fusion is an approach that generates fusion power with magnetic fields. Tokamak is a device that uses magnetic field to trap plasma in the shape of a torus. Plasma is a gas that contains free electrons and ions at very high temperature. The disadvantage of toroid is that it is very difficult to wind the wire. In an ideal toroid, the coils are circular. In reality, the turns of the toroidal coil form a helix and there is always a small magnetic field external to the toroid. So, this is all about toroidal solenoids. Happy learning and thank you.